Hi, thank you for attending this presentation of the CASFM 2020 virtual conference. My name is Isaac Allen, and I'm a water resources engineer with AECOM and the Compass joint venture. For this third and final presentation of this block, I'm pleased to be joined by Scott Hogan of the Federal Highway Administration Resource Center to discuss some of the 2D national efforts that have occurred over the last year. Scott's going to start off the presentation discussing some of the innovative approaches from the Federal Highway Administration, and then I'll wrap up with a few quick minutes on FEMA updates and things that they've been pushing over the last year. With that, I'll turn it over to Scott.
Thank you, Isaac. In this presentation, I will give you an overview of the methods that have been proposed to FEMA for delineating and evaluating floodways in a 2D model. But first, I would like to give you a little background on Federal Highway Administration's involvement and what has led up to the development of these methods. Federal Highway Administration has long recognized the benefits of 2D hydraulic modeling for detailed bridge hydraulics, and first starting using 2D modeling back in 1988, in fact. But back then, it took a tremendous amount of time and resources to develop and run a 2D model. So it was not widely used, but since then a lot has changed. Since 2012, Federal Highway Administration has officially recommended the use of 2D modeling for bridge hydraulics in our reference documents that you might be familiar with, HEC 18 and HDS 7. And then in 2013, Federal Highway Administration entered into a partnership with the U.S. Bureau of Reclamation in the ongoing development of the SRH 2D model for transportation hydraulics. And we also initiated a custom graphical interface in the SMS software package by Aquaveo. The use of 2D modeling has grown significantly, but there are still some barriers, and the application of 2D modeling for FEMA floodplain and floodway submittals is one of them. FEMA has approved the use of 2D models for a number of years, but the application to floodways and no-rise analysis has not been clearly defined. And as a result, on many projects, although 2D modeling is used for design, a 1D model has still been needed to support FEMA submittals. So now we work with all state DOTs on a regular basis, and this has been a challenge noted by many states. And so Federal Highway Administration is most interested in eliminating this need for duplicate effort, and we've been actively supporting further development and use of 2D modeling for FEMA analyses. So in 2018, we participated, I would say, in a group here in Colorado. It's a floodway work group that we called it was a consortium, I guess, of multiple agencies and consultants. And this group ultimately proposed methods both for delineating floodways in 2D models and addressing the resulting surcharge in water surface elevation. Our efforts have been well received, and as a result, FEMA formed an interagency project team, which I'll call IPT from here on out. This was over about a year ago, and the group was formed to assess what changes had to be made within the current standards and guidelines. And the new standards were available for public review in July and August, and I understand that these new standards and guidelines will be published or released from FEMA in the November timeframe, so stay tuned. So here's a quick overview of my presentation. I first want to highlight some of the modeling assumptions associated with 1D modeling and the reasons for moving to 2D modeling. Next, I'll present a methodology for evaluating surcharges in a 2D model, and then I'll introduce two methods that can be used for delineating floodways in 2D models. So to start with, many of us have been doing 1D modeling for so long that we tend to forget about how many assumptions or more simplifying assumptions that we make in 1D modeling. And more importantly for this discussion, how these assumptions can affect the correct delineation of a floodway. The main point of this table is to highlight how the need for so many assumptions is significantly alleviated with 2D modeling. And therefore, more accurate floodway delineation can be achieved with a 2D model. But I would also like to point out a few key assumptions that directly influence the accuracy of a floodway. Since a 1D model assumes that all flow is in one direction, the impact of blocking any lateral flow paths is not considered in a 1D model. And we learned in the 2D model that the impact of blocking these flow paths can typically result in localized rises that would not be represented in the 1D model. Also, a 1D model assumes a constant water surface elevation across each cross-section. And depending on the actual flow conditions and how accurately or correctly this cross-section is drawn, certainly this can introduce errors in the floodway delineation. With regards to flow distribution, it's important to understand that a 1D model redistributes flow at every cross-section based on the available conveyance area. Okay? So continuity of flow is not necessarily preserved in the overbank areas. So this certainly can have impacts on the floodway. The momentum of flow is also not considered, especially around bends and other abrupt changes, and this can affect the flow distribution. And one last point regarding channel geometry, and this is really not represented in this table, but it's important to note that although we do our best to represent the changes in model geometry and slope in a 1D model with cross-section placement, it's really challenging to represent all of the potential hydraulic controls in a 1D context. Throughout the rest of this presentation, I'll be using a case study developed for a project on the Elkhorn River in Nebraska, eastern Nebraska specifically. And many thanks to the Department of Transportation in Nebraska and their consultants, Felsberg, Holt, and Olvig, for sharing their project data with me. The 100-year flow in this reach is about 86,000 CFS. The model reach is about 9 miles long, with a floodplain that ranges between 1.5 miles and 3 miles wide. And the modeling effort for this project was primarily completed to support the design of roadway and bridge improvements along US Highway 30, shown here near the bottom of the image. This is the 2D mesh. Was developed using the SMS software interface for SRH2D. Some areas are more refined than others to represent potential hydraulic controls. And these were all generated with a new feature available in the free version of SMS 13.1 that is currently in beta. And it automatically delineates ridges and valleys. And these break lines then can be used by the user in developing a mesh. This mesh has about 87,000 elements, ranging in size from 3 feet in the vicinity of the bridge piers up to nearly 200 feet in the more wide open and flatter areas. The model was calibrated to a recent high flow event using measured high watermark data. And since I often get the question about how long an SRH2D simulation takes to run, for this case, for steady flow, it took 20 hours to reach a steady flow condition, and that 20-hour simulation took 12 minutes to run. So let's move into what I'm sure you're all more eager to hear about. So how are we proposing to evaluate floodway surcharge in 2D models? Well, as we move forward with 2D modeling, we'll ultimately no longer need to rely on cross sections for reference. So what is the alternative? Is there a better way? We thought about this quite a bit. And first of all, before we go any further, this image you see here is a 100-year floodplain result for this Elkhorn River model, showing velocity vectors and 2-foot contours in water surface. Right? So the Colorado Consortium group came up with the idea of using base flood elevation contour lines as evaluation lines and using averaged values along those lines. An average approach like this is consistent with the current state of the practice. It's what we do in 1D modeling. And the BFE, or base flood elevation contours, are already perpendicular to the flow, and their location then is not subjective. So they seem to provide a good reference, and we've not identified any roadblocks with this approach as of yet. Again, as I mentioned, for this example, I used 2-foot base flood elevation spacing, but for future application, I certainly would refer you to any guidance provided by FEMA when that's released in November regarding appropriate evaluation line spacing. In the bullets on the right, I've outlined the process in SMS and the SMS software for converting these base flood elevation lines to evaluation lines and extracting values along them. First of all, the actual contours or the base flood elevations are extracted to a shape file. Okay? And then once you have a shape file, it can be re-imported into SMS and converted to a cross-section coverage. Once you have this cross-section coverage, you can compute minimum, maximum, and average values for all model parameters along these lines. The cross-section coverage then can be used to generate summaries for the floodway simulations, or even proposed project conditions in performing a no-rise analysis. Before we look at the methods that we've identified for delineating floodways in 2D models, let's first look at the results of modeling the current effective 1D floodway in the 2D model. Okay, so this image shows the FEMA flood hazard map for this region. And if we extract the current floodway limits, as defined here, and represent that encroachment within the 2D model. The way we do that is in SMS SRH 2D, the floodway boundary, as you see here, is represented with a material type, or anything outside of that boundary is represented with an unassigned material type. Okay, this essentially turns the elements off during the simulation. This makes it easy to rerun a simulation with this material coverage, and then the results from that simulation can be compared with the base flood to assess the surcharge. So this image is the result of that. It shows a differential color contour plot, right, that represents subtracting the base flood elevation from the 1D, or the 1D floodway modeled in a 2D model. Say that several times. And so the red areas, all right, highlight or denote areas where the surcharge based on the 2D model result exceeds 1 foot. Now, I don't have the 1D results for you, but I can guarantee you that all of the surcharges in the 1D model were less than 1 foot. But in this case, you can see from the 2D results where the actual surcharges in some areas even exceed 2 feet and reach nearly 3 feet. Okay? So this is a good example. This result shows why the 1D modeling of floodways needs to be improved, and we can do a lot better in the 2D model. And this is not uncommon. We've seen this on several projects already in our testing. Now, if we add these base flood elevation lines, okay, to this scenario and average the results, so the water surface results within the floodway, within the limit of the floodway, we show those averages then in the table to the right. You can see in the left column is the base flood elevations and the average surcharge elevations. Okay, and then the differences. The red highlights indicate those that exceed the allowable 1 foot rise. Okay, so this is how it would be applied to a 1D floodway scenario. This method could also be used to evaluate a proposed project condition compared to a base flood. If you might be assessing a no-rise scenario, as long as the average values then showed no increase in water surface elevation. Well, now let's take a quick look at the two primary floodway delineation approaches that have been discussed amongst the IPT. These include an equal discharge reduction approach as well as a unit discharge approach, which is essentially the depth times the velocity. Equal discharge reduction method is the most consistent with the current 1D modeling equal conveyance approach. Okay, so equal flow area is removed from either edge of the floodplain until a target rise is achieved but not exceeded. Okay, it still uses a cross-section reference for evaluation, but the specific alignment of the cross-sections is not important. It's not critical, as the flow direction at each element is assessed independently and accounted for. So the cross sections are real simple, and they're just used as reference locations for computations. Floodway tools have been added to the SMS SRH2D interface to automate this process, but a few steps are still required by the user. Okay. A channel center line is needed along with bank definitions to prevent the floodway from encroaching or cutting into a channel meander. And a minimal set of cross sections, as I mentioned, are needed for reference. And then later on, they can be further interpolated for even more computation points. Floodway tools are accessed by right-clicking on the centerline coverage and selecting floodway. And the encroachment method is selected along with the appropriate mesh and results with a specified maximum rise, and then you can specify how many additional cross sections are interpolated for computations. And again, this method is all automated within SMS, creates the material coverage. You can run the results and easily compare the surcharge or compare the floodway with the base flood to identify the surcharge. And this is what the result looks like. It's another differential contour plot showing the resulting surcharge for the equal discharge reduction approach with a target rise of 1 foot. As you can see, there are a few red areas that highlight areas that do exceed 1 foot, but then as you refer to the table to the right, all of the average surcharges along those evaluation lines do not exceed the 1 foot allowable rise. You may also note there is one negative surcharge value in the third row, and negative surcharges will be allowed with 2D models, but certainly stay tuned and look to the final guidance from FEMA. There will also be some guidance from FEMA regarding allowable rise limits between evaluation lines, but that's still being discussed. And there will also be additional criteria for any insurable structures within the floodway. Any rise within their vicinity will certainly be held within the allowable surcharge limit. Now, the unit discharge in a 2D model can be computed by multiplying the depth and the velocity results. Okay? So the unit discharge really has little to do with the floodway rise. So this method is simply used to define a risk-based corridor that is then used as a floodway boundary. Okay? It's important to note that the specific unit discharge does not correspond to a specific surcharge. So it's up to the user to select a preferred starting unit discharge, evaluate the floodway, run the simulation, and iterate on that until the desired rise is achieved. You can see from the contours on the right, which are unit discharge contours, that there's certainly many areas that would meet the criteria of this selected unit discharge of 5 CFS per foot. But for this approach, all of the internal, I'm going to call them islands, are excluded, and only the outer limits of the unit discharge are used to define the corridor. Now, this unit discharge could be delineated manually, but we have developed an automated process within SMS that computes this, and similar to the other method, it trims the materials coverage to define a floodway boundary that you can then run a simulation and compare results. Okay. You do have to select the unit discharge method, the appropriate data sets, and specify a threshold, hit OK, and SMS essentially takes it from there. Here's the result for the unit unit discharge floodway method, and basically same kind of thing. You see a few areas that exceed the allowable 1 foot rise, but on average, as shown in the table to the right, okay, none of the average values exceed. All right, so this looks pretty good. Now we could continue to iterate on this to achieve slightly higher surcharges, but for this example, I just stuck with 5 CFS per foot. All right, as we start to close out here, I just want to show all three of these floodways on the same image. The red line shows the current effective 1D floodway, and we know that the rises were higher than the allowable 1 foot for that floodway. The two other floodways are shown, and honestly, I could probably continue to refine those to get a slightly narrower corridor, but it wouldn't be much. And in general, I can certainly say with confidence that any 2D floodway would generally be wider than the current 1D floodway. And before I close, I want to make it very clear that the floodway tools in this presentation are included in the free community version of SMS. Many of them are in the current version, and more will be added in the upcoming version 13.1. Please feel free to contact me with any questions on this. And if you're interested in additional resources or staying up to date on the latest 2D modeling tools and best practices, simply just send me an email, and you can then also sign up to participate in our bi-monthly webinar on 2D modeling best practices. So thanks again for listening. I wish you the best in future modeling endeavors. And now I'll turn it back to Isaac.
Thanks, Scott. With the last few minutes remaining, I'd like to talk about some of the updates from a FEMA side related to 2D floodways. As Scott mentioned, FEMA created an integrated project team, or IPT, to tackle some of the issues surrounding 2D floodways. The IPT had a wide range of membership, including several FEMA contractors, a number of FEMA regions, the Federal Highway Administration, Army Corps of Engineers, and CERT, as well as a number of individuals from the C2DC, which you've heard about over the last couple presentations. The purpose of the IPT was to define how FEMA was going to regulate and understand compliance for floodways based off of 2D models. The goals of the IPT were broken into two phases, with the first phase tackling short-term questions and issues, and the second phase looking to long-term issues and challenges to tackle surrounding 2D floodways. In the short term, FEMA was interested in looking at what allowable approaches could be used for 2D floodways. How were surcharges going to be evaluated, given the differences between 2D models and 1D models? Understanding where guidance and standards needed to be updated to clarify and identify how to regulate 2D floodways, as well as identifying where training was needed to help floodplain managers effectively manage floodways based off of 2D models. These questions were largely addressed over the last year during the IPT meetings that took place. In the future, FEMA is looking at additional questions that have more long-term implications. Those include revisiting whether or not an encroachment-based floodway is the best alternative or is the best approach, and if it's not, what alternatives might be available. And based off of that, looking at whether or not changes to the Code of Federal Regulations may be required based on how floodways may be defined in the future. As I mentioned, over the last year, FEMA has largely been tackling those short-term issues. And a big part of that has been drafting updated standards, guidance, and technical references to reflect some of the best practices and changes that have been discussed as part of the IPT. Over the last several months, those standards and guidance have been drafted and pushed through both review by the IPT as well as the public, and are now nearing the end of their cycle to be included with this November's updates to the guidance and standards. Please look out for additional presentations and information about the changes that were made to the standards and guidance, and reach out with any questions. The IPT isn't finished, and future meetings of the IPT, as I mentioned, will look to continue tackling those short-term issues as well as addressing some of the longer-term questions. Some main future considerations for the IPT will be looking at testing different floodway alternatives to see if there's an alternative to encroachment-based approach or just a refinement to encroachment-based floodways that could be done to better reflect the technology that we have. FEMA is also pushing new tools to expedite 2D floodway analysis in order to make it more cost competitive to do 2D floodways and recognize the advantages of that technology. and FEMA will continue to identify long-term needs and best practices to continue pushing floodway development. With that, I'd be happy to answer any questions, and thank you for tuning into this presentation.